Hello and welcome to our video. I'm Carlos, I'm from Plexus Lectures. I'm just covering the QCAA 2021 Physics Paper 1. This is going to be a new style of video we're trialing. We're going to do all of Paper 1 in one video, and what we're going to have in the description of our YouTube video will be quick links to timestamps, or I guess timestamps for the appropriate questions. Alright, let's jump into it. So question 1, leptons do not experience a weak force, strong force, gravitational force, and electromagnetic force. So this is ideally a question where I remember that I know quarks are governed by strong nuclear force, so I'm only remembering that. So I know by process of elimination that my leptons are hence not going to experience, because the key word here is not, are not going to experience a strong force. Now, a common trend in all our MCQ questions is some will involve some working and some are going to heavily rely on memory. So with those that heavily rely on memory, it's important to have a look through your syllabus. And I guess in the QCAA syllabus, it clearly outlines that this is going to be one of those key learning objectives that is relevant for your standard model knowledge. And I guess to pinpoint that learning objective out, you need to be able to contrast. So that's one of those, you need to be able to contrast the fundamental forces experienced by quarks and leptons. So this is a completely fair question to be asked, and you need to be able to differentiate, okay, what types of forces do leptons experience in comparison to quarks? All right, question 2. Calculate the initial horizontal velocity of a projectile with an initial velocity of 38 meters per second at an angle of 42 degrees. It's always super handy to draw out your scenarios. I'm going to draw a horizontal line for ground. There is my velocity vector. V is equal to 38 meters per second, and my angle is 42 degrees. So this, I want to figure out what the horizontal velocity is. So this component here, the Vx, I know my Vx is going to be equal to 38 multiplied by cosine 42. So how I get to that solution is I'm thinking of SOHCAHTOA. So I like to break mine down into my trig functions that I know. I'm trying to find the horizontal, which in this case, here's my angle, and that length is going to be the adjacent side, and that is my hypotenuse, the 38. And so that's going to give me a velocity for my x component of 28.24 meters per second. So that is going to leave me with B. Now, question 3, identify the correct formula for the mass-energy equivalence relationship. Unfortunately, again, that is just going to be brute force memory. There's not going to be a way to work through it, and that's just going to be energy is equal to mc squared. So again, this is going to be part of Einstein's mass-energy equivalence relationship. This should be committed to memory. We have flashcards on our website, so jump onto Plexus Lectures. But I guess one thing to remember in regards to this equation is that as per the syllabus, you need to know the equation as well as know how to solve problems using the equation. So an important tip or something to remember is that this equation expresses the fact that mass and energy are the same physical entity that can be changed into each other. Alright, so question 4. The diagram shows two charges, Q1 and Q2, separated by a distance of d. There is a force F acting between the two charges. Calculate the magnitude of the force acting between the two charges if d is halved and the charge Q2 is doubled. So it's important to know for all your formulas you're given in your formula book, you should be able to have a basic understanding of some of the relationships if you change a certain variable. Now, to dive into this question, I'm going to start looking for the appropriate formula. So a technique that I always use is, let's have a look at the variables we have been given. We've been given a charge, a diameter, and we're trying to calculate a force. So I always go, okay, this feels like it's going to be a magnetic field kind of question or fall under my electromagnetic kind of content that I've been learning. So I'll look in that particular field or area in my formula book. So the question or the formula I end up coming up with is F is equal to 1 over 4 pi E naught multiplied by capital Q multiplied by another Q, so that's our two charges, divided by R squared. And what that gives me is pretty much our formula that we're going to use. And we want to know the relationship between our first force in the situation where Q1 and Q2 do not change, they're constant, and same with diameter. So one thing that I'm going to get rid of or turn into a constant is Coulomb's constant, which is this region of our formula here, 1 over the 4 pi r E naught. So my new formula is going to be F is equal to K for Coulomb's constant multiplied by Q over R squared. So let's substitute this into the first situation before we've halved the distance between the two particles as well as doubling the charge of one. So F1 in the first situation is just K multiplied by Q1 multiplied by Q2, all divided by D squared. So that's our situation there. We're not going to add any values to these variables. We're going to add some values to the next variables. So in force 2, in that situation, we still have Kepler's constant. That remains the change. We're going to have Q1. So Q1 ends up being the same. It's going to be multiplied by 2Q because the charge of Q2 over here is doubled. So that's going to be 2Q2 divided by, now our diameter, this length from here to here has now been halved. So essentially we have done 1/2 D. So I'm going to write that as 1/2 D inside the brackets and square it. So I'm going to go through, simplify it a little bit further. So K still multiplied by 2 Q1 Q2 over 1/4 D squared. Then the next thing is I'm going to divide through that 1/4 and that 2 to simplify it to a term. So that's going to get me 2 divided by 0.25 is going to be 8. So it's going to be K multiplied by 8 Q1 Q2 all over D squared. So what I can now see is that between F1 and F2 all the way over here that we've simplified is that there is a change in magnitude by a factor of 8. So D is going to be my answer here. So it's 8F. So if I half the distance between the two particles, there's going to be a relationship change on the bottom of my fraction, as well as if I double my charge, there's going to be a relationship here on the numerator. So think about the relationship. You've got a squared there as well as you've just got a constant that's multiplied, and stepwise through it. All right, mesons are subatomic particles composed of one quark and one antiquark. To a T, straight off, that's my definition for a meson or meson. So question 6, electromagnetic radiation is extremely high frequency radiation emitted from the nucleus of radionucleotides. So to me, that is another form of electromagnetic radiation, but specifically that's talking about gamma radiation. How do I know it's gamma radiation? It's because it's talking about a high frequency radiation emitted from a nucleus. So that's gamma radiation. It's part of our electromagnetic radiation spectrum, but right now it's not the most correct answer. All right, B, the emission of energy as waves or particles, especially high energy particles that cause ionization. Again, to a T, it's not specifically the complete definition for electromagnetic radiation, but it talks in reference to ionizing radiation. All right. C, a wave of energy produced by an oscillating electric charge resulting in mutually perpendicular electric and magnetic fields. So again, this is partially correct, but let's read the next option, D. So radiant energy consisting of synchronized oscillations of electric energy and magnetic fields or electromagnetic waves propagated at the speed of light in a vacuum. So that speed of light as well is that extra definition there that's helping me pinpoint that D is going to be my correct answer. All right, so question 7. Normal force is the force acting along an imaginary line, parallel to the surface, perpendicular to the surface, opposite to the gravitational force, in the same direction as the gravitational force. So this question is, I guess, a little bit misleading in the two options. The first option that really calls out to me is option C, is that it's opposite the gravitational force. And option C is true, but it's not true in all circumstances. Whereas B, it's perpendicular to the surface. So what I would like to do is always draw back a situation, even if it's not purely based on like a mathematical breakdown of a trigonometric vector or any other working. So let's have a think. So here is just our surface, and here is our box. Gravitational force is downwards, so Fg. But our normal force is opposite to that, so Fn. So C is opposite the gravitational force, is true in this circumstance, but so is B. It's perpendicular. It's at a right angle to the surface. Now let's think of a slope. Here is our box sitting on a slope. That is our Fg, directly down. But our normal force, on the other hand, points opposite, or not quite opposite, points perpendicular to the surface that the object is resting on. So now I can say it's B, but it rules out C. So B is going to be the correct answer. C is correct, but it's not correct in all circumstances, like pointed out here on a slope. So question 8, the diagram shows two displacement vectors. Calculate the resultant vector above the horizontal axis when vector A is added to vector B. So this is just going to be a standard working question. I'm going to draw out my steps to solving this solution. So I'm going to draw the horizontal as a dashed line. So it's vector A added onto vector B. So vector B is going to be existing first. So I draw vector B in at an angle of 30 degrees. And it is a 30-meter displacement to this point here. And I'm adding on vector A. Vector A is completely perpendicular or up from horizontal, and it is a displacement of 20 meters. So what I'm trying to work out now is I want to know this position here. I need to know its angle as well as the length. So what I'm going to do is just take a trig approach. I'm going to call this R. R is going to be equal to the square root, so I'm just using Pythag here. The square root of, I'm going to call this length from here to here, Sx, and that's Sx of our original vector, right? Up here, Sx. So it's going to be Sx squared plus 20, because I need to, using trig, it's going to be 20 plus this value here, so Sy. And Sy is found from here, Sy. So in brackets, it's going to be the 20 plus Sy squared. So that's going to give me the displacement. So let's have a look. Same as that previous MCQ we had before, Sx, think about it, is going to be equal to 30 cos 30, because we're just using our SOHCAHTOA. This time we're using cos because our 30 degrees, that Sx is adjacent to the 30 degrees. And our Sy is going to be equal to 30 again, but this time we are using sine because Sy is opposite the 30 degrees. So our Sx is going to be equal to approximately 26 rounded up, and our Sy is going to be equal to 15. So that ends up getting us an R of 43.6 meters. So already we can rule out C and D. Now the next option is we've got to figure out the angle here. So again, I'm going to just use my basic trig. I'm going to use tan because I have the two side lengths. So I'll write on here in green now, that side length is Sx, which we already said is 26. This total side length here is, I'm going to get rid of all this other clutter so we can see it a little bit better. So our vertical side length is going to be equal to our 15 plus our 20, so that is going to be 35. So that angle, or theta in here, is going to be equal to, again, the tan inverse of the opposite over adjacent, which is going to be our 35 divided by our 26, which gives me a 53.4 degree angle. So that is going to be option B is the correct option. So some things to make sure going into this exam or going into any exam is that you know your calculators, you know your basic trig rules, because they're not going to be on any of your formula books. But the other thing is always check that your calculator is in degrees or is in the correct units when you're working with angles. All right. Question 9, the Bohr atomic model describes an atom as the smallest particle of any substance. Okay, again, that's a true statement. It's not as specific, but if all the other options are incorrect, I know A is going to be my choice. B, a small dense molecule orbited by electrons. That's true to the Bohr model or Bohr atomic model. Okay, C, electrons scattered through a sphere of positively charged fluids. Now, I don't believe this is going to be one of those ones that is on, or you guys might have touched previously, but this is actually, it's clearly not the Bohr model, but it's actually relating to the plum pudding model for our atomic model. So again, I'm going to cross that off. So I know definitely not C. All right, D, a small positive nucleus surrounded by negative electrons in set orbits of fixed energy. So D to me rings out to be the most correct of all the statements. A is a true statement, B is also a true statement, but D is the more correct of the statements that relates or describes the Bohr atomic model. All right, so question 10. Proper length is the length measured in the frame of reference where the object is at rest, in motion, accelerating, in motion but not accelerating. So proper length is option A. So where the object is at rest. So that is from the, I always like to draw back to the rocket perspective. Someone is in a rocket and the rocket is moving. This is a horrible looking rocket, but it is moving along, and then you have someone who's on the rocket and their frame of reference is at rest. But for an observer on, say, Earth, they are watching the rocket and the rocket is moving. So that is our L naught. So our L naught is the proper length, and you've also known, or you can calculate it in your length contraction formulas. It's L is equal to L naught multiplied by Lorentz factor, which is 1 minus the V squared over C squared. So L naught is the true length of the measured, or the true length or the proper length is the length measured in the frame of reference where the object is stationary. And so the frame of reference where the object is stationary is from the person who's actually on the object, and that is the at rest frame. Whereas the in motion is from the observer's perspective, watching. All right, question 11. Uniform circular motion occurs when an object is traveling in a circle at a constant. So, important thing to jump off before we read anything else about this question. It's got a leading statement here is constant what? Constant speed, velocity, or speed, velocity. So we need to be able to rule out 50% of our options straight off the bat. So a constant speed versus a constant velocity. Velocity is a vector entity. So if I draw a circle and I draw something at an instantaneous point at the top of my circle, in blue, it has a velocity going off perpendicular at that point. So that's its velocity there. But if it continues with its circular motion down to here, it has a velocity, again, perpendicular to that point where it is on the circle. So if it had a constant velocity, what that would look like is at that next position on the circle, it would be V pointing in that direction. So that already I know B and D are not correct. So how do I know that speed is correct? So speed is the average of velocities. It has no direction quantity to it. So it's an average velocity. So we can have our, if we go back to the original statement, it pointing off like that, v, and v here, perpendicular, that's going to be, the velocity is going to be the same, or the speed might be, say, 10 meters per second at each instance. But the direction, because remember velocity is a vector quantity, is going to be different at each instance. So that's how I know speed is correct and velocity isn't. All right, let's have a look at the second statement. Due to a force of constant magnitude acting in a parallel direction to its velocity. So if a force is acting in a parallel direction in our circular motion, I'm going to use the green pen now, and I'm going to draw it off. Parallel means it's acting in the same, or it's acting along that line. It can either be going that way or the opposite way. Now, I already know that the forces act inwards or perpendicular direction to its velocity. So I know it's pointing inwards, and that's going to be our centripetal force. So I already know that I can rule out B and D because of velocity statement, and now C I can rule in because the the force is at a constant magnitude acting in a perpendicular direction. It doesn't act in a parallel. So that's question C. All right, question 12. Calculate the maximum height reached by a projectile with an initial velocity of 15 meters per second at an angle of 30 degrees. So there's two ways to solve this solution. So there's a really quick abridged way, and this might be, I guess, relevant for those students who have done math specialist, because you might have been taught the formula. And then there's the way of using the formulas, which is a little bit more of a stepwise approach, using the formulas you've been given in your physics formula book. So I'm going to go with the quickest solution first. So always draw the scenario. This is an MCQ question, so whatever way you use or what solution you use doesn't matter because you're choosing the exact answer. There's no marks for working. So first and foremost, the situation, 15 meters per second. It's 15 meters per second. I'm going to draw my horizontal in, and it's at 30 degrees. So the ball is going to, or what was it? Is it a projectile? Is going to follow a path like that. And we want to find out the maximum height, that point there. So to find out that point, my first solution is going to look like this. So solution one, I'm going to use a formula called our height formula, and that is just going to be h is equal to the u. What do we know u is? It is our initial velocity, sine theta, that is our initial angle, squared over 2g. So g is going to be positive in this instance. So substituting my values in, u, it's going to be 15 sine 30 squared over 2 times 9.8. And that is going to get me, punch it into the calculator, 2.87 meters. So I already know, cool, that's solution, or answer A is the correct answer. Now let's go through solution 2. Solution 2 is a little bit more long-winded, but if you don't have that formula remembered and that we use in solution 1, solution 2 is going to be the way you approach it. So first and foremost, we need to find out the vertical component of our velocity. So this component here, we've been doing it for the last 2 kind of vector questions. So v, or I'm going to call it uy because it's our initial velocity, uy is going to be equal to 15 sine theta, or sine 30. Why is it sine SOHCAHTOA? So sine is the angle, and we're trying to calculate this opposite here, and that's our hypotenuse. So that's why it's sine. That's going to get us a velocity of 7.5 meters per second. Cool. What do we know about a projectile's path? We know once it gets to the top, I'm going to trace on here again, once it gets to the top of its projectile path, its vertical velocity, so the up or down velocity, is going to be equal to 0. So Vy is equal to 0 at the maximum. So Vy, I'm going to use this linear motion equation. Some people have probably heard them as kinematic equations. Gt plus Uy. So I know, set it equal to 0 because I want to know the time it takes to get to that point. G is going to be negative 9.8 multiplied by t plus our 7.5 meters per second. If my gravity is negative 9.8, it's acting downwards, and my initial velocity is acting upwards, it's going to have a positive value to it. So when you're working with these questions, make sure you assign the appropriate positive or negative value, because that's the direction quantifier. All right, so t rearranging, I end up getting 0.77 seconds. Now, the next thing I got to think about is I want to find out the displacement. So tip from previous MCQ is list the variables you have or you've been given, and also list the variable you're trying to calculate. And then what you can do is just jump into your formula book and then see which formulas have those variables that you're looking for. So I'm looking for SY, and it's going to be, I'm going to use my half gt squared plus my uy, again, my initial velocity, t. So I know g, negative 9.8. I know my time, 0.77 s. I know my initial velocity. And I'm trying to calculate my sy. So I'm going to punch those values in. Now, I don't quite have the room to write them. Oh, I should be able to. So 1/2 negative 9.8 times 0.77 squared plus our 7.5 multiplied by our 0.77 again. Remember that second one isn't squared. We get an SY equal to 2.87. And that's going to be option A again. So I guess the big run home point is projectile motion questions are quite common, either in short response or MCQ. So sometimes it is definitely handy to have this formula memorized before going into the exam. Because if you notice, solution 2 took us a lot longer to work through. All right, question 13. Calculate the orbital period of a satellite traveling around the Earth with a radius of 4.00 times 10 to the 8 meters. So I'm already thinking, again, let's go through it. What have we been given? And then can we look for a formula that we actually have? We're trying to calculate the period. We know period's denoted as t. We're given the radius, and we're told that we're going around Earth, so we know Earth has a mass as well. So I'm already leading into it. I'm thinking of Kepler's law. So Kepler's law is for orbital relationships around a solar body. So Kepler's law is t squared over r cubed is equal to 4 pi squared. Don't forget the pi squared. You can make an easy mistake and carry that through over gm. Sometimes we denote this half of the equation as k, equal to k for Kepler's constant. This case we're not going to, because we're worried about trying to figure out t here. And we have m, which m is our mass of Earth, g is the gravitational constant. So I like to always rearrange my equations before substituting any variables in. We're trying to calculate t squared, so t squared is going to be equal to 4 pi over g m, don't forget the squared, multiplied by r cubed. Another one, t is equal to the square root of 4 pi squared over g m multiplied by r cubed. So in this case, our r cubed, it's in the correct units. Always check the units you're given, because our gravitational constant is meters in its units, and our mass also has kilograms. So making sure you use the right units. So those two values, your g and your m, is in your formula book. R you've been given. So once I punch that into my calculator, I get a t of equal to 2518951.31. And I'll give you a second to have a quick think about what are the units in. Is it seconds, hours, minutes? It is going to be seconds. So remember, if you're working with meters for your distance, your gravitational constant has particular units. It's got meters, it's got force, as well as your mass has kilograms. If you're using all the standard SI units for that, it's going to get your solution in seconds. So what do? We're going to divide by seconds, divide it by 60. That gets you it in minutes. And then I'm going to divide that by 60 one more time. And that's going to get my minutes to hours. And I end up getting 699 hours. Now that is going to be 6.99 times 10 to the positive 2. So that's going to be option C. Now, if I forgot to do the pi squared, I'd done this previously when I was working through the question. I forgot to do the pi squared, and I ended up getting option B as my answer. So if you forget simple things, usually they'll put an option there, like B, for those students who forget that simple thing, and then you get kind of fixated, like, okay, cool, I got an actual exact answer. That is one of the options, so I have to be correct. Always go back through, have a quick scan through your working. Did you forget something? And again, have a quick glance at your question. Does it look reasonable at a glance? If so, then keep on moving. All right, so question 14 is moving electric charges in a magnetic field experience a decrease in charge, an increase in charge, a force parallel to the direction, or a force perpendicular to the direction of the magnetic field. So to think about this is, let's go through what's true and what isn't. So first and foremost, moving electric charge in a magnetic field doesn't experience a decrease in charge. It's going to maintain that charge. Nor is it going to increase in charge, so it's going to maintain it. So a force parallel to the direction of the magnetic field. So we're thinking of, here's a magnetic field. X's I always remember as into the pages. I think of digging up treasure. That means it must be into the page is the direction of the magnetic field line. If I then have an electron that comes into that magnetic field, it experiences a force to it. So if it experiences a force parallel to the direction of the magnetic field, that means it is going to go into the page. But I know, thinking about my Fleming's left hand rule for the motion or the force experienced by a left hand by an electron, I know using my pointer finger directing the magnetic field as well as then directing, the electron then directing the magnetic field, I get a force that is resultant upwards. So that force is not parallel to the magnetic field. It is actually perpendicular. So I know D is the correct answer. So again, this is just another example of one of those questions where drawing out the solution is the best way to remember certain rules that apply to certain situations. All right, which Feynman diagram shows an electron interaction with another electron? So we'll go through it in order. A is the answer. It is an electron reacting with another electron. So I'm going to go through the rest and describe what's happening so we can see. So in option B, we have an electron and a positron. So our electron, or this is called our electron and positron barter scattering. So we have our electron here, and then we have our positron here. On the diagram for C, what we have is an electron and a positron annihilation or annihilating into a photon, only to then pair produce. So here's our electron, here is our positron. It is annihilated and then pair produces. So pair produces an electron and pair produces your positron. And then finally, you have neutron decay. So an important note to remember about your neutron decay is you can be given your neutron decay either with your neutron denoted as N and your proton denoted as P positive. Otherwise, you need to know it is your quarks that make it up. So neutron is made up of an up and two down is usually how it will be demonstrated. They all got their signifying arrows. And then for your neutron decay, when it makes it a positron, the outwards you will have two up and a down. So that's another important thing to think about for your neutron decay. All right, question 16. The weight of a 5 kilogram object on Earth is, now weight is just the force experienced by that object, so 5 kg, or even taking it a step back, force is equal to mass times acceleration. F is equal to 5 times 9.8. This one I shouldn't need to put in my calculator. I can clearly tell that's not correct. Nor is that one. 51 is too high. So 49 newtons. All right, so we're on question 17, the final page. So I hope we're tracking all right for time. So question 17, electrical potential energy is, so we've got another 4-option one that we just got to read through every single option. Common trend we've noticed with the other ones is some are partially correct and some statements are completely incorrect, and then there's a more correct statement. So it's important to always read these options when you're given a definition type MCQ. So the first one, electrical potential energy is intensity of an electric field at a particular location. So it's describing more or less to me just the strength of an electrical field at an instance. Now, so I'm going to put that as uncertain, but I'm going to head down the lines of not too sure, or not going to be the correct answer. Difference in potential that tends to give rise to an electric current. I already know straight off the bat that is the definition for voltage. Cool. So I'm going to leave that as that. All right, capacity of electric charge carries to do work due to their position in an electric circuit. So that sounds like the definition for me. Electric potential energy. So we think of an electron's position and its ability to do work. So not doing the work itself, because we're thinking of potential energy. So I'm already thinking C is my most correct answer here. Work done on an electron and accelerating it through an electric potential difference of 1 volt. So this describes a completely different scenario, a specific scenario where an electron is actually doing work. So D is neither, or D is not going to be my answer. So C is my correct answer here. Again, we have another definition answer, question 18. A gravitational field is the net gravitational force per unit mass at a particular point in space. So again, that's similar to option A in the previous question. It's just telling us the kind of gravitational field strength. It's just a definition for the field strength, that it's the strength in a particular point in space. So a particular point, that's leading me towards the strength in space. So energy stored in an object as a result of its position relative to another object. So to me, that is just GPE. That could be GPE of an object being held close to another larger object with mass, and it's not moving, but it's holding potential energy. All right, region of space surrounding a body in which another body experiences a force of gravitational attraction. C is starting to sound really good to me. So I'm going to lock in C as the answer. I'm going to read D. So position in space where objects experience a force or acquired potential energy as they are worked into that position. So again, this is more or less describing GPE in comparison. So it's definitely describing a portion of what a gravitational field is, but it is going into the definition of GPE, or putting work into something to move it. All right, a spaceship with a velocity of 9.0 times 10 to the 7 meters per second is measured to be 125 meters in length by an observer at rest. Calculate the length of the spaceship as measured by somebody on board the spaceship. So this is a length contraction question. So length contraction, we have our formula. We used it previously in one of the MCQs when we were discussing the definition for the proper length. So L0 times the Lorentz factor 1 minus V squared over C squared. So the important thing is which one is our proper length and which one is our contracted length. In this case, L0 is our proper length. So we are trying to calculate L0. We have our velocity here and we have our contracted length. So L in this case is going to be 125 m. Now, if I'm uncertain or if I ever forget which one's which in a scenario, because it's quite easy to be inundated with other information. You're remembering a lot of other content as well. So don't ever feel disheartened if you cannot remember what the exact formula is, or sorry, you have the exact formula, but remembering which one goes to which. So I would do trial and error in this case. If I'm uncertain, I might put the 125 as my L0 here. And what I would notice is that 125 gets smaller, but I know the one thing I do remember is that there's length contraction. So the person on the spaceship should actually have a longer spaceship than the length of 125 by the observer. So I know, okay, now I just got to switch the LO and the L. I have them incorrectly placed. So LO is our proper length. So we have 125 is equal to LO multiplied by 1 minus on top V squared 9 times 10 to the 7 squared over 3 times 10 to the 9 squared. And then I will rearrange that and substitute it, or rearrange it, and I get my LO as 131.04, and that's going to be option B as the correct answer. In this one, I've kind of done it slightly a little bit different. I always like to rearrange my equations before doing the substituting in, because if you're working the steps out, it's a little bit extra, or a little bit more you have to write when you're working with such large values like 9 times 10 to the 7, 125, and your speed of light. So I recommend rearranging it and solving it. When it's an MCQ, your working does not matter. The only thing that matters is getting the right answer. So you can work it out however you want. All right, question 20, final question of the MCQs for paper 1. So a photon electron with a kinetic energy of 2.5 times 10 to the negative 19 joules is ejected when a photon with a frequency of 1.3 times 10 to the 15 hertz is incident on the metal plate. Calculate the threshold frequency of light required to eject the photoelectron from the metal plate. So this is a photoelectric point. So we have our work equation is the one that I'm thinking about using. The reason I'm thinking we need the work equation is because it's asking for the threshold, or the threshold of frequency of light required. So the frequency is telling us we need to calculate a little bit extra. So what I'm going to look at is, what's my formula for photoelectric? So it is EK, the energy of the ejected electron, is equal to HF minus the work function. So the work function itself is also made up of another formula. We can get to that a little bit later down this track. But what information have we been given? We've been given the EK. Oh, keep on getting it mixed up. The EK, which is equal to 2.5 times 10 to the negative 19. We have also been given what the frequency is. Frequency is equal to, 1.3 times 10 to the 15 hertz. And I'll put my joules here. Now, another thing is, it's fairly common, they've done it in previous papers and future papers, using, instead of joules, electron volts. So make sure when you're working with these equations, you use the right units. Because what is our H? H is Planck's constant, and Planck's constant has joules as one of the SI units in there. So in this case, I'm happy. My EK is in joules, so I don't need to convert it. And Planck's constant is in your textbook or your formula book, and that is 6.626 times 10 to the negative 34. So I'm trying to figure out what the work function is. So again, I'm going to use it this time. I'm going to first rearrange my equation. So I'll write it again with some room. Keep on doing the K quite large. So I will go down a bit. So EK is equal to HF minus W. My new statement is going to be HF is equal to EK plus W. Therefore, W is equal to HF minus EK. I know what my HF is and I know what my EK is, so W is going to be equal to 6.626 times 10 to the negative 34. That's Planck's constant multiplied by the frequency the incidence frequency, otherwise known as, and that is 1.3 times 10 to the 15 minus our EK, which was the energy of the electron ejected, 25 times 10 to the negative 19. Now you can get different questions. EK, you might get it in evolts, or the other thing is you can get the velocity that electron is ejected with, and you can calculate just from the velocity and the mass the kinetic energy of an electron, and that's the energy it's been ejected with. So we get a W equal to 6.1138 times 10 to the negative 19, and that is in joules. So that's not quite our answer yet. It's not in hertz. So we know the work function is equal to HF. We can rearrange that to get our F is equal to work divided by h, and that's our w from up here, and our h is Planck's constant. And what we end up getting is 9.23 times 10 to the 14. And so I'm going to have a look back up. 9.23, we have a 9.2 as option C. So that is our correct answer. All right, we'll move on to the short response. All right, before we jump into the short response questions, I guess I want to flag for some of the written responses, like question 21, we're going to have online our annotated notes, which are the notes that we use for creating our videos. So linked in the description of the video, feel free to click it. There'll be the annotated notes as well as for the MCQs showing our working through the steps. So for some of these short response, I'll just talk through it a little bit longer and maybe write down some minimal notes. All right, so let's jump into it. So question 21, explain how transformers work in terms of Faraday's law and electromagnetic induction. So I guess the first thing to start off with is, what is a transformer? So a transformer is going to be a device that can transfer, so keyword is transfer here, electrical energy from one device or one current, alternating current, to another circuit. So I guess to better phrase that is, you have two circuits. You'll have a coil here and a coil over here, or the coils may be superimposed in one another. One of them has a battery pack connected to them, and it is an alternating current. So it's going to produce an alternating current. And what that alternating current does, so thinking about how to answer this question in a stepwise fashion, one of the marks is just discussing that an alternating current, so your alternating current produces a alternating magnetic field. Or in other terms, this is a magnetic flux. So produces a mag flux. Okay, so step 2, what is that mag flux doing? So we're thinking in stepwise fashion. So due to that changing magnetic field or that magnetic flux, we're going to create or induce an EMF into another coil. So the mag flux induces an EMF into another coil. And so that's going to be creating, or step down or step up, depending on the type of coils you have set up, as well as the voltage. So the next one is just mentioning that your induced EMF is proportional to the number of coils as well as the rate of change of the flux. So that will be, so it's not one of the formulas I believe you get given, but it is one of the formulas you would have come across throughout the year. Your VP, NP over your NS. So that's just exchanging or showing that you can change the voltage induced based on just the voltage of the primary circuit, or you can also change the voltage based on the number of coils. So definitely hop online, check the link in the description, and that's going to have more of a stepped out or the written actual response. Or again, go onto the QCAA website, and that's going to have to a T their 1 mark or their mark per dot point. All right, so question 22. I'm going to highlight as we go through. So a planet is orbiting a 3.38 times 10 to the 31 kilogram star. The radius of the orbit is 4.23 times 10 to the 8 kilometers. Calculate the average speed of the planet. So first thing to think about is, or I guess this is my approach for any kind of question, no matter short response or MCQ, is to think about what topic does it fall under? Because if I don't know how to solve this question, if I can pinpoint what topic it falls under, I can then start looking for appropriate formulas. I know this question is going to fall under orbital or gravity, orbital, and motion. So I'm going to start looking in that form or that area of my formula book. The other thing I start thinking about is, what variables have I then been given? I've been given the mass of a star. I haven't been given the mass of my planet. I've been given the radius at which my planet's orbiting. A quick thing to flag with that is it's being given to you in kilometers. So let's convert kilometers to meters. The conversion for kilometers to meters is going to be times 10 to the 3. So that is going to be 4.23 times 10 to the 11, because I'm just tacking on that 10 to the 3 to that 10 to the 8. And that's going to be in meters. So I'm just going to write that down now. So we know we're working with the SI units. All right, so continuing through, I'm starting to look for formulas that have those variables, that have mass, velocity, because that's what we're trying to calculate the average speed, as well as the radius. So what I'm ending up doing is I'm looking for the first formula, F, or force is equal to mv squared over r, and my second formula is going to be F is equal to gmm over r squared. So the reason I know to go straight to these formulas is because doing previous questions, you start to realize some of the habits or techniques that they give you with specific questions. In this case, we have to take a simultaneous approach because we've got a couple of variables that we want to cancel out, or we need to set equal to one another. So in this case, I can go through and tick, okay, mass of the planet. I don't quite have that, so I'm going to remove the tick, but I'm trying to determine the velocity. I have the radius. I know what g is, that's a gravitational constant. I know what capital M is, that's our solar mass, or the mass of the planet we're orbiting. And we do have r again in this case. We don't have the mass of our planet, but we have it over here. What I do know or realize is when we set these two equations equal to one another, I can cancel out the m. So let's work through that. We're going to set the two equations to one another. So mv squared over r is equal to g m lowercase m over r squared. Let me get rid of the r on the left hand side. So that's going to be mv squared is equal to g m over r. So I've done the right hand side multiplied by r and just cancelled out the r at the top. And I get left with a single r down the bottom. All right, let's move the mass now. So moving it to the other side, I divide it through. So v squared is going to be equal to g m over r m. The two m's cancel out, so I can remove them from that side. So there we go. We've solved our issue with having the mass of our planet. Continuing through, we have v is equal to root g m over r. And that's going to get us our velocity for our planet, or its orbital velocity. The tip that I like to do is always rearrange your equations first before you substitute any values in. That makes it easier or minimizes your error of carrying an error and saves you a lot of writing. So now we have our g, we have our m, and we also have our radius. So I'm just going to substitute that in now. So g is our gravitational constant, which is 6.6. That's a horrible looking 6. 6.67 times 10 to the negative 11 multiplied by the mass of our star, which is 3.38 times 10 to the 31, all divided by our radius, which is the radius over here that we've calculated in meters, which is 4.23 times 10 to the 11. And once we punch that in, we're looking for to the nearest whole number. That ends up being 73005 meters per second. And we'll write that in the space down below. And so that's our solution for question 22. Some things to remember is if you don't know what topic it is, or if you don't know where to start, think about what the topic this question falls under. Then have a look at the variables you've been given and see if you can match up some formulas, and then you can hopefully work it through from there. All right, let's continue on. Okay, so question 23. The diagram shows a metal rod with a mass of 10 grams and a length of 8 centimeters suspended in a uniform magnetic field of 0.50 teslas. There is no electric current through the metal rod when it is in position 1. So position 1 is this image here. So it looks like it's sitting at rest, okay? When a current of I is passed through the metal rod, it moves to position 2 with an angle of 40 degrees to the vertical. All right, cool. And let's quickly read over. Determine the magnitude of the current required to move the metal rod. So before we jump through this question, I'm going to quickly flag some important things. We flagged it in question 22, which was looking at your units. 10 grams is not our standard unit, so we convert our 10 grams to kilograms. So I'm just going to write up the top here, that's 0.01 kg. And our length here is in centimeters. I'm going to convert that to meters because we're always working with meters. So that's going to be 0.08 meters. Now let's break down the situation that we have here. So at the resting position, we only have gravity working downwards. So an Fg, or F weight, is another thing working on the rod. We also have the tension in the rope. That is going to be F tension. So when there's no current applied, we know a metal rod is going to stay in that same position, in that magnetic field. But when we have a current carrying rod within a magnetic field, we know there's going to be a force exerted on that rod. So in this new position, when it has a current flowing through it, we still have a force, or we now have a force that's pushed it across. I'm going to relocate that force vector and locate it here. So we have a force that's pushed it across and given us a resultant 40 degrees. We still have the force of gravity, Fg, on our situation. So we have the force due to magnetic field. So F mag is what I'm going to call it. Or I might just refer to it as Fm. So I'm going to work through on the other page, but I want you to remember this or break down your situation step by step. So we have a current carrying wire and a magnetic field. What do we know about current carrying wires in a magnetic field? There is a resultant force that acts on them. Here we can have a look. There's a force that's pushing that rod towards the left, or sorry, towards the right. So we need to figure out what F mag is. So I'm going to redraw the situation. So we have our rod that is on a rope at 40 degrees. So this is a horrible diagram now. 40 degrees down here. I'll try to straighten that out. And then what's happened? We have two forces acting. We have our Fg, which is always going to be acting on our rod. Fg is going to be equal to our 0.01 multiplied by 9.8. And then we have our other force, which is our F mag here. Our F mag we can calculate using trig. So F mag is going to be, think about what variables we've been given. We've been given this one here, which is adjacent, and we're trying to calculate, so that's our adjacent, we're trying to calculate the opposite. So we can use tan in this case. So my formula for F mag is going to be equal to, so I'm going to write it out. TOA is the one we're using, so tan is equal to opposite over adjacent. We are trying to calculate the opposite, so we're going to have Fg, which is our adjacent, multiplied by tan theta, or tan our angle, which is 40. So let's continue writing it through. F mag is equal to 0.01 times 9.8 times tan to the 40. So sweet, we've already calculated out what the force is that's working or pushing our metal rod that's carrying a current towards the right. And that is a force of 0.08223 newtons. So that's important. I need to confirm this is in newtons. We did make sure we converted our length, or sorry, our mass to kilograms. And so we can go from here. Now the next thing is, we've got to remember that a force can be induced. There's going to be a formula based on certain variables, the strength of the magnetic field, as well as the length of the wire that's in the magnetic field and the current that's through it. So our first situation is, what's our formula we're using? It's going to be F Bill sine theta. So what's our theta in this case? Before we jump into any of the other variables, our theta is going to be 90. Why is it 90? I'm going to go back up and have a look at our situation here. So I'm going to clear off these forces now. Initially, our magnetic fields are running through like this. And what ends up happening is our wire is sitting at a 90 degree to our magnetic fields. So I know it's Bill sine 90. What's sine 90 equal to? It's equal to 1. So our formula for F mag is going to be equal to Bill. All right, next thing. Let's rearrange our formula to calculate I, because that is our variable. We're trying to determine the magnitude of the current. So we know what the magnetic field strength is. It's written out before. B is equal to 0.5 Teslas. We know what Fmag is equal to. Fmag is equal to 0.0823 newtons. And our length, we converted that from centimeters to meters, is equal to 0.08 m. Remember, I always like to rearrange my equation first before I substitute any of my variables in. So Fmag, I'm going to just drop it down to Fm, is going to be divided by BL is equal to I. And then we can substitute our values in. So we have I is equal to 0.08223 divided by 0.5 multiplied by 0.08. We get our current equal to 2.055794 continuing amps. Let's have a look at what they want. It wants it to one decimal place, so it is going to be 2, or I'll change my pen back to red, 2.1 amps. So a quick overview of this situation. We're working with multiple, fields of our physics that we've learned throughout the year. Realize that your rod is sitting in a magnetic field initially with no current. But when the current is turned on, there is a force that happens due to current carrying wire sitting in a magnetic field. So what can we determine? Can we determine that magnet or that force initially? Yes, we can, because we've got the force of gravity. We know the angle that that rod's sitting at. So take time, work through, redraw the scenarios if that works for you. All right, moving on. All right, so question 24. The diagram shows a 1.5 kilogram object here on an inclined plane with an angle of 30 degrees on the horizontal. The object experiences a frictional force of 4.5 newtons. So that's that 4.5 newtons pointing in that direction. So this is very similar to one of the MCQs that was given earlier on this paper, just talking about your normal force, or just, getting you to recall on what the forces are that an object on an inclined plane can experience. So let's quickly draw through all the forces that have been explained here. So we have a force of gravity, Fg, otherwise sometimes known as Fw. That's going to be equal to the mass of the object, 1.5, multiplied by 9.8. We also have the force of friction, which is parallel to the surface, which is going to be F of F, and that's going to be equal to 4.5 newtons. And we've given it a direction because, again, force is a directional vector. And then you also have the normal force, which your Fn is just the perpendicular force from the surface or the slope that your object is resting on. So the question is, if we continue reading it, it wants us to figure out what is the magnitude of the net force acting on the object. So first and foremost, our net force acting on the object, if I'm to draw that as a vector, is going to be the force acting down the slope. So I'll draw it a little bit shorter so we can kind of see what's happening. So blue is our force net. So our force net is going to be equal, I'm going to write down below, F net is going to be equal to the x component. So if I draw the x component in green of that Fg, so Fgx. So Fgx minus the force of friction that's working in the other direction. So let's think about how we're going to calculate that Fgx. So Fgx is an x component of a triangle or of our force of gravity. So if I draw the other component to it, which is the normal force essentially acting on it, or the force here, which is our right angle, is going to make up our Fg. So we have an Fgx. And so that Fgx, if we put our angles in, this is going to follow the same suit as what we had before. This is going to be 60 degrees up here. Why is it 60 degrees? Because we know this angle here is 60 degrees and it's perpendicular, and this is a parallel line here, if that makes sense. So That's 60 degrees. In here is 30 degrees because we know it's on a right angle. So to figure out first and foremost FGX, it's going to be equal to FG, which is this hypotenuse length from here to here. We're going to use our sine, and it's going to be FG multiplied by sine 30. The reason it's sine is because I'm using this angle here. I'm using SOHCAHTOA. Sine is opposite over hypotenuse, and we're trying to calculate FGX, which is this length here, and it's the opposite. So I've drawn it on a fair bit. So now I'm going to punch that into my calculator, and what I end up getting for that force is 7.49. So I know, I'm going to clear it out a little bit now, make it a little bit more neater. I know there is a force from the gravity, because it's on an inclined plane, we're going to get an x component to it. There is a FGX, which is equal to 7.4 newtons acting downwards. Our net force is going to be Fn, which is going to be, as we've said down here, FGX minus Fx. So if I restate that again, Fn is equal to our 7.4 newtons minus our 4.5 newtons. And that gets us our 2.9 newtons. So there's a force of 2.9 newtons acting parallel to the slope to pull the block downwards. And again, always check what the units are they're asking for in newtons to one decimal place, so 2.9. And that's going to be question 24. All right, so question 25. The graph shows the centripetal forces required to keep objects with different masses in uniform circular motion with a constant speed and constant radius of 20 centimeters. So this question is fairly straightforward from the get-go. What we know is we have a constant radius of 20 centimeters. From this point forward, whenever I see units that aren't in my SI units or standard units of meters, I'm going to always make sure I convert them at the top. 0.2 meters is that constant radius that we're working with. And we're going to have differing masses. So when you're given a question with a graph, always check what your x and y axes are. So here we have object mass, and we have on our y centripetal force, so force experience. The question is now asking us to determine the speed of the objects. So we know from reading the question again, every single object is spun with a constant speed, no matter what the mass is. So there are two solutions to go about this, and I'm going to show both solutions in this worked example. So first solution is to go, so solution 1, I'll put a line down the middle of the page. So solution 1 is to realize, okay, what equation can I use? So I'm always going to say the same thing. Figure out what your variables are, and then tick them off, or go looking in the formula book for a formula with the same variables. So we're looking for first, we have force, we have a force variable, we have a mass variable, we also have a velocity variable, that's what we're trying to calculate, and we also have a radius variable. And we know this is going to fall under gravity and motion, and the formula we end up getting is F is equal to mv squared over r. It's the perfect formula. It ticks off all the variables we've been given in our equation. So we are trying to solve for v. So what I'm going to do is first rearrange the equation, and then I'm going to look at the variables that we've been given. So we'll start off with that. So rearranging for v, we get f r is equal to mv squared. We move over the m, f over m is equal to v squared, and I'm going to do, next step is v is equal to root f r over m. All right, so this is our new situation. So let's have a look. Do we have a force, a radius, and an m? So our radius, as we've said before, is 0.2 meters. It's constant, it's not changing. Our force, on the other hand, to me, this graph looks like a linear relationship. As you increase the object's mass, its centripetal force is also going to increase at a constant gradient. So I'm going to choose any of these, and it's not going to make much of a difference. So I'm going to choose this point here because it's clear cut. At 0.2, kilograms, the force is 6. So F is equal to 6 newtons at a mass equals to 0.20 kg. So I'll put my newtons here. So we can substitute that into our equation now. V is equal to the square root of 6 times 0.2 over 0.2. That's going to get me a velocity of 2.449 meters per second. So an important thing to remember is the reason we changed our units from before we had centimeters up the top is if we don't change our units around, we're going to get some really weird, or mainly not the most or not the correct value at the end. So we've got meters per second. Now solution 2 is the method that they want you to work when it comes to the QCAA. So they've given you a graph. They want you to realize some parameters of this graph. So your graph, we've already talked about it being a linear relationship. So your linear relationship is a relationship of y is equal to mx plus c. I'm going to get rid of the plus c because it starts at 0, 0. When you have no, or when the object has no mass, so I'll change my pen color. When the object has no mass, it has no force. And then I'm also going to use this point here. So let's first think about it. What is our y? Y is force. So we have F is equal to, what's our gradient? Our gradient is going to be, I'm just going to call it G for gradient for now. And our X is mass, and that's represented by M. So let's have a look. We can use the same formula as what we used in the previous example. We're using force is equal to mv squared over r. We can rearrange this slightly so we can break it. So F is equal to v squared on r multiplied by m. These two are the same statement. But what we can see now is here's our m variable, which is the m here, and we also have our g. That's our g, our gradient. So our gradient is equal to, so gradient, that slope above, is equal to v squared over r. So whatever we find that gradient out to be, we can then rearrange to solve for v because we know our radius is constant. What's our radius? 0.2 meters. So what's our gradient? Gradient is equal to, so I'm just going to call it gradient, is equal to the change in y over the change in x. In our case, our y is our force, and we're going to use 2 points. I'm going to use the same point up here, the force of 6 newtons, and we're going to use our intercept down here, 0, 0. So 6 minus 0 over 0.2 minus 0. We end up getting a gradient of 30, and then we can have our statement. Therefore, 30 is equal to our v squared over r, which therefore 30 is equal to v squared. We don't know what that is. R is equal to 0.2. I can rearrange this. I end up getting v is equal to the square root of 30 multiplied by 0.2, and that equals 2.449 meters per second. So we got the same exact answer, 2.4, one decimal place. So the reason why solution 2 I can argue as a more accurate approach is because we've used our gradient. Our gradient is more or less the average of the whole entire slope because it's taken into account our beginning value and our end value here. It's not a true gradient, so to say, or the gradient of the line of best fit, but is the closest in comparison. All right, so have a look at those two solutions. There are multiple questions that we've worked through previously in the MCQs that you can have two solutions approach and see what works best for you or what makes more sense. All right, so the final question for paper 1 is question 26. So a physicist has identified the absorption spectrum of an unknown atom. So when we're looking at the absorption spectrum, we are looking at different wavelengths of light here for an unknown atom. The diagram shows the atomic energy levels for 3 different atoms. So atom 1, atom 2, and 3. And so there are different energy levels for each different atom. Determine which atom is most likely to be the unknown atom. So the thing to recall here is that we know as you change from a different energy level or an energy state, an atom will then release that energy. So if we started our ground state down here, so that's ground, or otherwise known as N1, 2, 3, 4, 5. If we change between an energy level, we release that energy. And we also know from before, or from your earlier content covered, energy can be expressed as H multiplied by F. So energy is equal to H multiplied by frequency, or otherwise, you can think of it as your frequency is equal to the speed of light divided by the wavelength. Therefore, your energy is equal to H multiplied by C on your wavelength. So with this idea, we can determine if you have an energy change from level 3 to 2 or 2 to 3, you can then determine, knowing what Planck's constant is, because that is a constant value, that's our 6.626 times 10 to the negative 34, and our speed of light, which is 3 times 10 to the 8, we can figure out the wavelength here. But we're working in the opposite direction. We've been given our wavelength, and so what we need to do is predict the energy, because we want to then go back, find which atoms have the right energy jump or energy shell change. So let's go through that and talk through the problem a little bit more. So step one is going to be figuring out what each wavelength would be energy in joules, energy-wise. So step one, I'll just write it as S1, and we're going to start off with our top. So 421 is the wavelength. So 421 nanometers. So remember, our formula is energy is going to be equal to Planck's constant multiplied by speed of light over the wavelength. Now, the thing to remember is that we need to convert our units to standard units. Nanometers is not in meters, so we need to convert that to meters. So what we need to do is nanometers to meters is times 10 to the negative 9. So when I write my formula now for energy, energy is going to be equal to H. So I'll just do a large brackets here so we can write it a little bit neater. So inside Planck's constant, 6.626 times 10 to the negative 34 multiplied by our speed of light, 3 times 10 to the 8, all divided by our wavelength. Now remember, our wavelength is 421 nanometers, but to convert it to meters, we times it by 10 to the negative 9. So there's a conversion, there's a conversion table in your workbook or your formula book. So you will be able to get that information there and practice using that. So we end up getting our energy as 4.72 times 10 to the negative 19. And the thing that we need to think here is that this energy is in joules. The reason it's in joules because one of the SI units in our Planck's constant has joules in there. So we need to remember our energy here we've calculated in joules. But in this example, we're working with EV, so electron volts. So that means we need to convert our joules to EV. So how do we do that? Have a look in your formula book there. It tells you that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So what we need to do now is divide this by 1.6 times 10 to the negative 19. And that's going to get me 2.95 EVs. So I'm going to quickly run through the others and get that done. So for the second wavelength, 491, that's line 2. Our energy we end up getting is equal to 4.05 times 10 to the negative 19 joules. And that's going to be also equal to 2.53 EV. And then finally, our other nanometers or our other wavelength that we end up detecting is 5231 nanometers, and the energy that corresponds to that is equal to 3.8 times 10 to the negative 19 joules, which is equal to 2.38 electron volts. So a common thing to think about, or a trend for your other revision and practice as you go through, is think about what happens to the energy as the wavelength increases or the wavelength decreases, because they're common questions to think about, or it's a common thing to have committed to memory when you think about relationships between products or constants in your equations. So, all right, now what we've got to do is we've got to look for an energy change between certain atoms that correspond to that. I'm going to save time and go through example atom 2 because atom 2 is the answer here. So what we look for is we have our energy N1, 2, 3, 4, and 5. So I'm going to look anywhere from 1 to 2, that is 3.6 to 14. So that's going to be about an 11 EV. And anything from 1 onwards is going to be greater than 11 electron volts. So that's not going to be my energy level. So my next thing is I'm going to look at 3.6 here to 1.22. So I'm going to punch in 3.6 minus 1.22, and that's going to correspond to one of my energy levels. And that energy level is going to be my 2.38 electron volts. Another one is going from energy level 2 to 4 or 4 down to 2. That's going to correspond to 2.53. And we know from 2 to 5 or 5 to 2 is going to be 2.95. So we've found here in atom 2. Atom 3 gets very close. The first level here is 2.28, which is 0.1 off. And we have 2.52 is the next one, and then 2.95. So it gets very close, but the examples they're going to give you are specific and going to be precise. So that's why atom 2 would be the answer. So my answer would be atom 2 is shown, and then would be just stating the energy levels. So 522, and it was 422, and 322. And then you can also make sure you show or state the energy levels for each and subtract them through so you can see the change or what is released. All right, so that's going to conclude our video for paper 1 for the 2021 physics exam. Thank you for watching.